What is a wave? Well, waves are, as we talked about, everywhere. Uh, if you even look at these pictures, you can see here we see waves in the water. This one we're talking about sound waves, light waves. You can see waves. Sometimes you can't see them. Sometimes you can feel them, hear them. But waves are all around us. A wave is a regular pattern of motion created by a vibratory disturbance. In other words, something that is kind of like moving back and forth can create a wave. Um, like when you talk, you can kind of feel your vocal cords on your neck, like you can kind of feel them vibrating, and that's where that sound wave is coming from when you speak. Waves can move through matter, meaning like they can move through the water, through the air, through solid things. Um, and then some waves are special and can travel through a vacuum, which is a place where there's no matter, and that's like space, like outer space. A wave transfers energy. So waves are very closely related to energy. Waves carry energy. So when energy is moving from one thing to another, it's waves that are moving it. You can see the energy being carried by the wave. Um, the movement of the wave is actually movement of energy through the matter. So, like here in this picture, we see this wave, but what that really is showing is that there's energy that started here, like that motion energy, that mechanical energy, it's transferring through the water. So that mechanical to mechanical transferring from the finger to the water. Okay, so we talked about how waves can travel through matter. We call that a medium. A medium is a substance, gas, liquid, solid, so basically some sort of matter through which a wave travels. When a wave travels through a medium, it causes the particles in that substance to oscillate. Oscillate is basically means going back and forth. So you can almost think of like a pendulum. Oops. Ooh, got too far. Like like a swing, like on a swing set, how you go back and forth, that's oscillating. And then when it's done oscillating and it's at rest, that rest point is called the equilibrium. So you can almost imagine that down here in this picture, like if this was showing like waves in an ocean, if the water was perfectly still, it would all kind of line up along this central line. And that's its equilibrium. But as you can see, when the waves are there, it's going above it and below it. Okay, so to be very clear, a wave does not transfer matter. Waves do transfer energy. So, not matter, just the energy. And down here, you can kind of see this blue dot is representing like a piece of matter. Imagine if this was water, maybe that blue dot is like a leaf in the water. When the wave goes by, it lifts that leaf up and pushes it and then kind of drops it back down. But notice that the leaf isn't going back and forth at all. It's just kind of going up and down. So it's the energy that's moving through it, not the matter. Okay. So periodic waves are the nice, pretty waves that are very regular. Like you can see that like this red one, it's kind of like the same kind of wave all the way through, different kinds of waves here. They call that periodic waves, constant speed, oscillating regularly. Okay. Waves can be categorized. So we're looking here at electromagnetic waves and mechanical waves. So two major categories, electromagnetic and mechanical. Electromagnetic waves are waves created by oscillations of electric and magnetic fields. So these are electric fields, magnetic fields. These are things we can't necessarily see because it's not matter. It's it's these fields that exist and are around us. Obviously we wouldn't just you wouldn't see them. And anyways, these kind of waves carry electromagnetic energy. So you might remember when we talked about different kinds of energy, electromagnetic was one of them. And we also called that one light energy or radiant energy. But electromagnetic energy is more than just light that you can see. There's lots of different kinds. So they do not require a medium. So these are the special ones that can travel through outer space. They can travel through a vacuum. And as we said, light is an example of electromagnetic wave. Mechanical waves, on the other hand, they require a medium, a solid, liquid, or gas, and they're created by this movement of an actual object. So it's not through the fields, it's like physical waves. Let's see here, they transfer energy through a series of collisions. So you can almost imagine that pool of water where like the hand came down and disturbed it and created that ripple. The initial particle in the medium is disturbed, poke in the water. The particle collides into other particles and they collide into others, and that's how the energy is kind of transferred through it. And then sound is a type of mechanical wave. So light was electromagnetic, sound is mechanical. Looking further into mechanical waves, we can then divide those up into three different kinds: transverse, longitudinal, and surface. Transverse move perpendicular to the direction of the wave. So the direction of the wave you can see is moving over here to the right. Well, the wave is actually going up and down, up and down, up and down. So this up and down motion is perpendicular to that wave. So I like to think of this as like if I had a piece of rope like tied to a door handle and I'm moving it up and down, or like a jump rope. That's like a transverse wave. So here we are again talking about how the direction of the wave is going one way, left to right, and the particles are moving up and down. So here's that perpendicular. And then we have our parts of it. So the top of a wave, this is where we call the crest. The bottom is called the trough. Here's an example. This person actually has a rope. They've got it tied to a tree though. And you can see how they're moving their end, they'll move their end of the rope up and down, and the wave will actually go from left to right, moving towards the tree. Longitudinal. Longitudinal are like slinky waves. This wave is still going from left to right, but if you kind of look at it, the lines in here, they're not going up and down. They're actually going left and right as well. So they're going parallel, the same direction. So here you can see it again. We have the wave starting from here, going this way. Particles are actually moving back and forth. I always think of a slinky. Oops. Go too far. So the area where it's compressed, like pushed together, that's known as a compression. The area where they're spread apart, that's called a rarefaction. So they kind of correspond to the crest and the trough. So like the rarefaction would be like the trough, and the compression would be like the crest. So here you can see it. If it's this, the crests and the compressions kind of line up together, the troughs and the rarefactions. Yeah, and here is our slinky. You can see how the wave in the slinky, they get compressions and they have the rarefactions. We're going to do an example with a slinky maybe later this week. We'll see. And surface waves. Surface waves are like a combo. And they're called surface waves because they only travel along the surface, like land and water, and only the particles at the surface oscillate. Ocean waves are surface waves, water waves. Okay, so here we go. You can see that in a surface wave, the particles oscillate parallel and perpendicular. So it's almost like they're making like this little roundish motion because they're kind of being pulled up and down and left and right at the same time. Notice how it's kind of staying in that little area. It's not really going with the wave all the way down. All right, the part you've all been waiting for, graphing. It's not as hard as it sounds. When you're graphing waves, the easiest kind of waves to graph are transverse waves, those like typical wave shape that we talked about. Because and then here you just need the y-axis and the x-axis. In this case, the x-axis stands for either time per second, or it could stand for the distance, but the y-axis stands for height. All right, some of the parts that we've talked about already. We know that the crest is the top of the wave, the low point is the trough, and that line that kind of cuts it through the middle is known as equilibrium or the rest point. A wave cycle, this is a new one, is one complete path of the wave. I always like to measure, like I start with a point at the equilibrium and go up to the crest, down to the trough, back to equilibrium, and that is one cycle. So here in this picture, we have two complete wave cycles. Now, some of the things we measure on the waves are the amplitude, the wavelength, and the frequency. The amplitude is simply the height of the wave. And you could measure this in two places because of the way waves work. You could look at the equilibrium to the crest or the equilibrium to the trough, but make sure you're starting at equilibrium and going, up, or starting there and going down. And it's usually measured in meters. So that's the amplitude. And here it's stressing, do not measure the distance from the trough to the crest. Don't go all the way down. That's too far. You just want literally equilibrium to crest. All right, when we're looking at mechanical waves, those ones that go through have to have a medium to travel through. If something has a high amplitude, it has a high energy. If it has a low amplitude, it has low energy. You can almost think about like how that kid with the rope on the tree, if his wave if he moved his arm a lot and used a lot of energy, he was going to get really tall waves. But if he like didn't use very much and barely moved his arm, he'd have low. And then in sound, the high energy means it's going to be loud. So high amplitude is loud. You guys have probably heard of like bands adding amps. Those amps increase the loudness. Wavelength. Wavelength is the measure of one complete wave. So it's measured in meters again, just like amplitude is. And we're literally like, we talked about wave cycles. Literally, you're just looking at the distance from the beginning of one wave to the end of that wave. You could measure it here, like where it's getting ready to go down to the trough and then up to the crest and then down. Or you could start at, one crest and go to the next crest. A lot of people do that because it just seems to be easier to measure from crest to crest or trough to trough. But any of the wave works as long as you're doing just one complete wave. If we're looking at a longitudinal wavelength you would measure by looking at like the center of one compression to the center of the next compression, or rarefaction to rarefaction. When you're looking at longitudinal waves, it's hard to measure the amplitude and frequency, but wavelength is something we can measure fairly easily. And frequency. Frequency is a rate. So it's the number of times of wave cycles in 1 second. It's measured in hertz. So here we have on this axis down here, it's measuring seconds. So this whole thing is looking at 1 second, and I can see that 2 waves passed in 1 second. That's my frequency. And so since it's 2 waves in 1 second, my frequency is 2 hertz.